Okay, so thank you for the invitation. And I have just realized that I am missing differentiable function. It's not about starting. Anyway, so this is a joint work with Valeria Vanica, and it is this is the okay. So this is the summary. So I will start with the analytical problem, which is nothing but to look for continuous functions which are nowhere differentiable. Then I will speak about the geometric problem, which is the evolution of some curves in R3, which are in principle are related to the evolution of vortex filaments like the smoke rings. And the equation of this model is rather simple. It is the velocity chi is the curve, t is the time, so the velocity, the derivative with respect to t of chi, is in the direction of the binormal, and the speed, the absolute value, is the curvature. So it's curvature times the binormal, something rather simple. And to fix the ideas, I am interested in kind of singular objects, in particular, how does one corner evolve? Because in a one corner, the curvature is a delta function, and the binormal in principle will have a jump, so it is not clear which would be the curvature times the binormal. And not only one corner, but even several corners, what is the interaction of these different corners. The third guy is the PDE problem, and it will have as an underlying PDE is a dispersive type of equation, which is the focusing 1D cubic NLS, and it will be related to the curvature. So if I'm interested in corners, then the initial condition will be delta functions, that they will be always at the same distance. I mean, the corners will be located at the integers, and with some amplitudes determined by these coefficients AJs. And related, making a connection with this PDE and the 1D cubic NLS is a guy in between, which is the Schrödinger map, which is nothing but the PDE that the tangent vector of these curves satisfy. And indeed, there will be a fourth part of the talk, which is if there is any connection of all this with turbulence. And we have a kind of small conjecture, which is that the answer is yes, and more in particular, we are thinking, or we believe, that this is related to the turbulence generated by non-circular jets. More concretely, I will speak about something which is called multifractal formalism, which is related to Frisch and Parisi. And I will say very little about something, another kind of word, which is intermittency, that also appears trying to describe turbulence. So let's start with the analytical guy, which is Riemann's function, Riemann's non-differentiable function. And it is the one you see on the screen. So it is just a trigonometric series, a Fourier series, where the frequencies are just the squares. The variable is t, and it is divided by j squared, so that this function is obviously continuous. I guess probably in 1860 that this was continuous was not so simple, who knows. But the question was if this function has derivative anywhere. So it's attributed to Riemann that he conjectured that this function, although it is continuous at every point, it has no point of differentiability. The first, so this was, you want a beautiful analytical problem that was studied among others by Hardy, and in the sense that the very first steps and positive steps were given by Hardy in 1915 using the so-called Hardy-Littlewood circle method. But the problem was not solved until Gerbert. So Hardy essentially proved that Riemann was right, but there was a bunch of points that he couldn't give an answer. And then we had to wait until 1960, who Gerbert, that at that time was an undergraduate study, proved that Riemann was wrong. In fact, when you look at rational multiples of pi, and you take p and q to be odd, the derivative exists. And what is even more interesting is that the derivative has always the same value, which is -1/2. All right, so I also need to introduce a quite similar, quite related guy, which is the complex version of Riemann's function. And it is just the same kind of trigonometric series, but now instead of using the sine or the cosine, I use the complex exponentials. And there is a D key here because it was Duistermaat, the one who started to look at it and stress the issues about the properties of the graph of this function. So the graph is, so this is one parameter, time, and this is a complex number. So the graph will describe a curve in the plane. And you will see the picture in a minute, and it will be obvious from the picture that this curve has some kind of fractal behavior. All right, so now some pictures. This is nothing but Riemann's non-differentiable function. So the first conclusion when one sees this picture is at the time of Riemann, they didn't have this kind of facilities, right? Because if you look at this picture, you immediately see that there are points where you have a derivative, which of course are these ones. And as you see, the derivative is it goes in this direction. As I said before, is -1/2. And you see that it appears here and appears here. So, and also you could imagine that there is some kind of fractality or weird behavior with this function. Let me also stress that, for example, in this point, the 0, right, because it is 2 periodic. So the reason why it is not differentiable is because this is nothing but the square root of t. And that's the reason why at this point, the function is not differentiable, while in these ones, it is -1/2. So this is in half of a period, 1, right? Now, what I promised, which is Duistermaat's approximation, which is the phi sub d. I'm using the d here, I'm sorry. And this is the graph of the function. So now, well, we have a curve. And what happens now at 0? Well, you see, there is a tangent for, say, t positive, and there is a tangent for t negative. But the reason why this does not have a tangent is not because it was not differentiable for t positive. It is because the two tangents are different. So this is a small remark, but I guess it's quite relevant that there is a jump to analyze the analytical guy, I mean the function itself, to go from the analytical guy to the geometric guy, which is the curve. So what happened in the period when t was 1? And now you see there is some kind of a spiral here and another spiral here, but in fact there is a tangent, and the tangent is 0, 1. You have these spirals. This picture is not that good. We will see a few pictures later on that look much better. So in these points, you have a tangent. All right, and this will become kind of I don't know if important, at least I would say interesting later on. So it was Jaffard who really studied Duistermaat gave a lot of insight of. He analyzed quite a bit the function, did a lot of asymptotics around these points and around all the national points, but really the first theorem regarding the fractality of this curve is more than the fractality, something different I'll mention in a minute. It was a fact. And in fact, what he proved is that the so-called multifractal formalism due to phase separability, it holds true in the particular case of Riemann's function, I mean the one of the real part, but the theorem applies also for the imaginary part. I mean for the cosine of the sum. I'm sorry. So now, what is this multifractal formalism? So first of all, I have to start speaking about what is called the spectrum of singularities of a function f, which is nothing but the Hausdorff dimension of a set E beta, and E beta is just the set of points T naught, in this case the period 0, 2, where f is beta Holder, right? So you classify all the points in the interval 0, 2 according to the exponent of the Holder exponent that the function satisfies at that point. Here, of course, the Holder exponent is the sub in alpha of f in C alpha, and because for me beta will be smaller than 1, then this is, in principle, this will be any polynomial, but in here will be nothing but f of t naught. So I look at the difference between f of t and f of t naught, and I want to find what is the best alpha I can put here, right? And this is the Holder exponent. So let me introduce another guy, which is Weierstrass. In fact, Weierstrass is the one that claims that the so-called Riemann's non-differentiable function is due to Riemann, but there is nothing really written that we can say that Riemann proposed this function. In any case, Ballesteros was interested in the problem, and he couldn't prove what Riemann was saying. So he invented his own example and constructed the so-called Ballesteros functions, which are now, again, it is a trigonometric series, but now you see the frequencies are lacunary. So you give a number b, and you look at the frequencies b to the n, and then you have to put accordingly some amplitude such that you have continuity, but when you differentiate, then at least formally there is no way that the series is convergent. And then he proved that indeed these kind of functions are nowhere differentiable. From the point of view I am interested in this talk, this issue about the lacunary series makes a difference. And in fact, these functions are not so interesting. And in here, really what happens is that the Holder exponent is just 1, which is the log of A divided by log of B. And in fact, from a geometric point of view, this is just a monofractal. There is only one possible Hausdorff dimension. Anyway, so let's move forward. In order to say more why Friese and Parisi were interested in these kind of multifractal definitions. And the reason for them was to try to understand some time series that were obtained by Antonia Hoffinger, Gagne, and Anselment in an experiment in 1984 about the turbulence of duct flow, I mean, or a pipe, if you want. A circular jet, but where you the turbulence has already been developed. So they made very precise experiments, and then in the analysis of the time series, they computed many moments of the so-called structure functions. And there was no simple way of trying to fit this data with any kind of theory, in this case, the so-called cosmological theory. So then Friese and Parisi introduced something different, and it's more or less as follows. So before I had defined the df of beta, remember this was the spectrum of singularities, beta meaning the Holder exponent. And now I am going to define another guy related to f, which is this eta f of p, which is nothing but you want the regularity of the function measured in terms of the Bezoff spaces in this way. These Bezoff spaces, I mean, the definition of Bezoff spaces is very much related to what it is called the structure function, which is the one analyzed by these people. So then you have two different numbers. One is the dimension of the E beta, the Holder exponent, and you have this other guy, which is the sub in S of for the function such that f belongs to this fancy Sobolev space. So then it was so in a sense to compute the momentum, the different momenta of this structure function. So this is the related structure function. It's not so easy. And then what Friese and Parisi proposed was that a way of measuring this momentum was to do the Legendre transform of this eta f. So then, given this number, you generate this other number, which is the Legendre transform. And then what Friese and Parisi conjecture is that the two guys are the same. And in principle, this was proposed for general functions, but it was not proof for anyone. It was Jafar, the first one that gave a proof that at least for Riemann's non-differentiable function, this identity was true. And in fact, in this case, you have a continuous interval for possible Holder exponents, not as in the case of Weierstrass function, where you had only one. And this beta goes in between 1/2 and 3/4. So you see, at some point, I will start to speak about PDEs, and the beta is meaning some kind of singularity. So it's the Holder regularity. So what I am saying is the kind of singular behavior of this phenomenon, of this function, is not given just by one exponent, say some kind of blow up given by some power, right? But instead you have a continuous interval of possible blow up rates that makes a difference with respect to many of the known examples of dispersive blow up in dispersive equations. So as a consequence, because he proves that these two identities are the same, then the multifractal formalism is true for this particular function. But you see, there was nothing, this was just an analytical object, a function, and there was this idea by Fritz Parisi, and Jafar computed that it was the case in this particular example. But there was no reason to make a connection between Riemann's non-differentiable function and anything related to, say, turbulence or at least fluid dynamics. And this is the main result that I want to talk about in this talk today. That finally we made a connection between the two problems. In fact, in our case, we will consider as geometric objects, we will consider, in order to obtain the Riemann's non-differentiable function, we'll be looking at polygons of many sides, but because the binormal flow has different kind of symmetries, if you can go from, for example, you can go from the circle, which is a particular solution, to the helix, and then you can also construct helical polygons such that the torsion is given by a rational number. And then you can construct also some kind of Riemann's non-differentiable function. But in this case, the Riemann's non-differentiable function is a kind of an arithmetic progression. Instead of having the pure squares, you have the squares of an arithmetic progression. So we wanted to prove both things, the multifractal formalism and the intermittency of these guys. The intermittency of these guys for the Riemann's function was recently proved by, I will mention later on, the reference. So in our case, we had to prove it. And in fact, it was not enough just to use directly, we couldn't use directly Jafar's result. We had to open the books of his proof. And in fact, we used some improvements due to Skolkov and Chamizo-Ubis, and in a way, we found a shortcut. So the final outcome is going to be that this identity holds true not just for the function where d is 0 and c is 1, but for all these, say, new Riemann's non-differentiable functions. Anyway, so now the geometric guy. So it's, I already introduced it, is the binormal flow. So chi is the curve, depends on two parameters, the time parameter and the spatial parameter s, that is in fact arc length. And it is in coordinates is given just by this wedge product. So this is the derivative of the curve. So this is the tangent vector. And we will see in a minute that this cross product gives you immediately curvature times the binormal. In order to do that, let's look at what is the equation for satisfied by the tangent vector. So you differentiate here with respect to s, and then it gives you 0. So when you differentiate here in s, you obtain TSS. So this is, after a minute of thinking, you will realize that this is nothing but the Schrödinger map onto the unit sphere. And why the unit sphere? Because this flow immediately preserves arc length. Because if I do the inner product with t here, then this is 0. So the length of the tangent vector is preserved, and I will assume it is 1. And that's the reason why I use arc length parametrization. So now let's go back here. This is a tangent vector, and this is in fact TS. So this is the curvature times the normal. So I have to do the wedge product of the tangent with the normal, which gives me the binormal. So this is nothing but curvature times the binormal. And the examples immediately are, of course, the straight line, which nothing happens. It stays a straight line forever. Then the circle, that stays a circle forever, but it moves up or down depending on the orientation. So these are always the curves which are need an orientation. That in terms of fluid mechanics is related to the sign of the circulation. Of course, this is related to, say, the bathtub vortex or the tornadoes, if you want, and this will be related to the smoke rings that we will see in a minute. But as I said before, it's very easy to go from circles to helices. In fact, these are nothing but the traveling wave solutions of the tangent vector. And what we are going to do later on will be to approximate these circles, but polygons of many sides, regular polygons, and the same with the helices. And we will try to follow the trajectory of one corner. This is really what I am interested in. All right, so now some pictures. let me erase this. This guy is Dustin Kleckner, that he was working at the time of this movie. He was working in Chicago, and with William Irvine, they obtained they made a very famous experiment on noctide vortices. But I'm not interested. I'm just looking at this nice video where we see this is a circular jet, and as you see, you generate the vortex by putting bubbles here. I'm sorry, bubbles here, and then the bubbles go to the minimum of the pressure, and well, you can think that this is moving like a circle and it's not changing its shape, right? So these are the circles. So now let's try to put something more interesting, if you want, which is the one you see here. So this is what I call a non-circular jet. Why? Because the nozzle is non-circular. You have it here. So let's move it again, and let's stop it at some point. So you see, we have that later. So in fact, at the beginning, it's kind of nothing is really seen, but suddenly you see a configuration here, right, more or less, which is like the starting configuration inverted. But later on, you essentially see the shape of the nozzle. So you have, say, these tips, one here, so you have some kind of triangular symmetry. And then later on, this axis, say this one, and this one, had been switched to the previous configuration, right? Okay, so now the axes are this one, and this one. This is very well documented in the literature about non-circular jets. That was very much on fashion during the 90s. And it is called the axis switching phenomenon. So the next movie is already done for our model, the binormal flow, and is as follows. In fact, a simulation like this one was done by Bob Gerard and J.S. Metz based on some code determined by Batke, and Batke was his thesis. He was a student of Shorin, and this was at the end of the 80s, and the result by Gerard and Metz is of 2011. Anyway, so this is what Gerard and Metz saw. That you started with a equilateral triangle, and there is a time where you recover the equilateral triangle. And what De La Hoz and I did was, okay, let's see what happens if I try to follow the trajectory of this corner here, and this is the trajectory, the one you see here. So let's see, for example, what is this spiral you have in the middle, which is quite likely half of a period. So let's go back. Pay attention in the right to see when I have to stop. So we are almost there. And you see now what's going on, right? Oops. Here. So this is the axis switching phenomenon I was mentioning before. And this is in half of a period. So now what happens if I want to detect one of these corners? For example, the one that I will appear here. So let's keep moving. Yeah, for example, here. Well, let's go to the next one because it's cleaner. Yeah. So now you have 1, 2, 3, 4, 5, I think it's 6. No, this must be 9 sides. It's not completely clear. But in any case, you capture another polygon. So in half of a period, you have the same triangle with the axis switched. In half of a period, you will have a polygon with 6 sides, which will be in 1/4 of a period, which will be this guy. This guy has 6 sides, and so on and so forth. So this is very much related to the Talbot phenomenon. That is something very well known in the setting of the Schrödinger equation, and something I will not talk about. But the final outcome is that when the time is rational, then you recover a polygon, in this case a skew polygon, that has as many sides as the denominator, except that from time to time, which is, for example, when q equals 1, which is half of a period, then instead of having 6 sides, which will be half of a period, you still have 3. And the reason is that there is some Gauss sum that becomes 0. Right, which was this, and this is in these spirals here. Anyway, so as I said before, what I really wanted is what I want is to approximate, say, the nozzle, the circular nozzle, right? I imagine I have my jet, the one I showed you before, and I generate the corresponding vortex ring. But I want to approximate it by this kind of shape, which is a polygon, in this case, of 15 sides. And now this is the evolution. I look at one point. So the point is starting here, it will be moving in the straight line, as you see here. But on the other hand, when you look at the one of this polygon, it creates this fractal, if you want. That is not exactly the same as the one we have seen in the case of the equilateral polygon. The main difference is this angle. In this angle, it's getting closer and closer to pi over 2. That is something I should have said in the example by Duistermatt, that the angle that appeared was really pi over 2. Here we are getting closer and closer to this pi over 2. So that means that if I make the capital M, meaning the number of sides of the polygon, going to infinity, then in the limit, I will obtain something that will not disappear. Of course, I have to renormalize size because the size of this guy is becoming smaller with M. But if I make the sum, then at the end, I capture a guy that does not disappear, and it looks very much as the picture that I showed regarding Duistermatt, right? And this is the theorem that Valeria and I have proved that this is indeed the case, that if after you do the corresponding renormalization, meaning the corresponding sum or dilation, then this guy tends to Riemann's, is in fact a small variation of Riemann's non-differentiable function. And the same thing happens if instead of starting with, say, a circle, you start with a helix, and you make again, so the helix has the property that the tangent vector is periodic. So now you have, this is the period, say, and you generate the corresponding helical polygonal line, such that in here, if I'm not wrong, this is also has 15 sides. This is simulation done by Sandeep Kumar, and this is in a paper that we wrote, De La Hoz, Kumar, and myself. And what we did in this case was to follow the trajectory of one corner. So let me show you again. And as you see, this you have essentially the same kind of phenomena. And this is what I said at the beginning, that, I said before that this is related not to Riemann's non-differentiable function, but something similar where the quadratic faces have changed by the squares of an arithmetic progression. So these are the people who I have mentioned. Batke, that created the code that was used by Gerard and Smets in 2011, and Peskin and McQueen, by the way, I didn't say it, is they observe this kind of fractal behavior in their experiments regarding the aortic valve, where they use the binormal flows as a model to describe the geometric properties of the aortic valve. So then after the work by Gerard Smets, there was this paper with De La Hoz that we followed the trajectory of the corner, and after some insight, we made the connection, at least at the numerical level, with Riemann's non-differentiable function. But this was mainly at the numerical level. And there is another work that I will mention in a minute. And the last one is about the helices, that it is part of Kumar's thesis that was defended in 2020, in the middle of the pandemic, by the way. So now the PDEs. So I already introduced the first one and the second one. So now I have to introduce the third one. And the third one is the cubic LS. And this is done through what is called the Hashimoto wave function. And remember that we are interested in the skew polygonal lines. So that means that the tangent vector will be a sequence of points that in our case, these tangents will be fixed at infinity. There will be two vectors, unitary vectors, a plus and a minus, plus at plus infinity, minus at minus infinity. And this polygonal line will be fixed. This is something that has to be proved. It is given at time 0, and it turns out that you can prove that this is fixed for all times. Then, in terms of the Hashimoto wave function, that I will define it in a minute, which is essentially the curvature, it will be just a bunch of delta functions that, and because the polygons I consider has the same length, then the corners are located, say, at the integers. And and of course, these AJs will measure the curvature and the torsion of the skew polygonal line. The curvature will be the modulus, and the torsion will be the phases of these coefficients. And so I need, in a sense, well, I'm saying that this goes to two flat lines. And in fact, I need more than that. I need that I have some decay in the Fourier coefficient, some weighted decay. And indeed, this is because this is an algebra, as we'll see in a minute. So once you have these guys psi, it's once you have the curvature and the torsion, you integrate the Frenet frame. But typically, because I'm working with delta functions, I cannot compute the absolute value of a delta function. It's much better to use what is called the parallel frame, which is this one I have here instead of the Frenet frame I introduced before. Now, finally, what is the psi? Well, if you give me t, if you give me capital X, I generate the t. Given the t, I construct the frame E1 and E2 and alpha and beta. And now I generate the complex function alpha plus I beta, psi. And in fact, this psi, that if you want to write it in polar form, is because it's a complex number. If it's written in polar form, then the modulus, what I said before, is the curvature, and the derivative of the phase is the torsion. This is as long as the curve is regular. If in the case you have corners, then as I said before, this is not a good way of describing the curvature and the torsion, but the one I have just written in the previous slide. So, well, then what did Hashimoto do? Well, he computed, he given, say, a smooth curve, you define this complex value function, and now you wonder what is the equation that this psi satisfies, and it turns out that after 1.5 pages computation, you end up with this well-known nonlinear dispersive PD, which is the cubic NLS. As remember, is one dimension in S, t is time, and cubic nonlinearity is here. You can put plus or minus depending on the geometry. In our case, because I'm working with the vortex filament, the geometry is the one of the sphere, so it is the Euclidean geometry, and is the focusing. You could have changed the sphere by the hyperbolic plane, changing the underlying geometry. And then in that case, you obtain the focusing case. This is just for information. It's not something I'm going to use. But then you have this extra guy that plays a crucial role for the analysis, which is this real number A of t, which is reflecting the gauge invariance of the equation. Because I am giving the curvature and the torsion, right? Then in order to construct the curve, I always have the freedom at each time of where to choose the origin of coordinates of the normal plane. So then, of course, this had to be implemented by the trajectory of one point. But in principle, at the level of cubic NLS, I not only have one equation, but I have a kind of a class, equivalence class of equations. And this is something that I can choose from. I have this freedom, and it can help me in order to understand this nonlinear equation. That remember that I'm looking at very singular objects. So in particular, I will look at objects which are the curvature is constant. It can depend on time, but for a given time, the curvature is constant, and they are infinite filaments. So the typical L2 norm will be then infinite. So I cannot use the standard theory. I have to go further than that. And in particular, for example, in the case of one corner, it was done by Babke that essentially the curvature has to be he proved that the curvature has to be A over square root of t, and the torsion has to be S over 2t. So this is the solution at the level of cubic NLS, and of course this is infinite. So the usual L2 theory, because S has to go from negative infinity to positive infinity, cannot be used. So you need something beyond L2, and this is something that I started with Anna Vargas many years ago in the early 2000s, and there has been plenty of literature after that. In fact, even I will mention a result in this direction. But there is at the level of the PDE, and as I should have showed you when I saw I showed you the picture of the evolution of the equilateral triangle. It's very easy to see that for times very close to 0, the evolution of a corner has a self-similar behavior. So it is a fundamental thing then to understand what are the self-similar solutions of the binormal flow. And here you have more than one possible self-similarity, but you choose the one that preserves arc length. So this is the right one. So then you compute what is the ODE that G has to satisfy, and immediately you obtain this. And from this, it's very easy to see, for example, as I said, this was proved by Batke in his thesis, that the curvature has to be a constant. All right, but okay, so I expect, and this is at the end can be proved, that the initial condition associated to this G should be the one of one corner, but then that it is located at S equals 0, and then at a later time, I will see the evolution of one corner, which is one of the questions I posed at the very beginning. How does one corner evolve? And okay, so I have to see, of course, it is just to understand what is G of 0, but G of 0 is nothing but this. But this was the curvature times the binormal at 0. And that is the free parameter, A naught, and B of 0 is something that I have to determine. If I have in a sense, I have the freedom to choose the initial conditions of the Frenet frame, the tangent, the normal, and the binormal. This could be the identity, but then what is the relation between the free parameter A naught? So in particular, you see what is this thing geometrically? You see the torsion is S over 2 is 0. So close to the origin, this is going to be a circle of radius 1 over A naught. But then what is the angle? The angle is really at infinity. So I have to make the matching between, if you want, what is the angle of the corner with A naught. And this is it. So as you will see in a minute, the angle is seen at infinity. It's really the behavior of G at infinity, that this goes to, at infinity goes to one unit vector at plus infinity and another unit vector at negative infinity. So this is the typical connecting problem in ODEs that can be very, very tricky. And but in this case, you have a precise answer. And this was something I proved with Susana Gutierrez and Judith Rivas back in 2003. And this is the closed formula. This is the angle, and this is the curvature, say, at the origin. Of course, once I'm not speaking about the connecting problem and I am able to give a closed formula, immediately you say, well, this is because the equation is completely integral. And in fact, this is the case. That the reason why we can compute this is because the equation, I mean, this is the reason. The different issue is how you compute it, because it is not straightforward. This is a fact. In general, if at the end everything I'm telling you is related to real fluids, you don't expect the theory to work for big A naughts. So you only need really what happens asymptotically for A naught small, and then to obtain the asymptotics of this guy in terms of so I'm saying take the angle very close to pi. That's what I'm saying. Then to obtain what is the relation between this value and the angle, this is not so complicated. In any case, to prove this formula is not straightforward. And in the paper of 2018 with De La Haute, we found a different approach to the one followed with Gutierrez and Rivas. And the interesting thing regarding this new approach is that we found what for me is kind of the fingerprint of the singular behavior of this. You want the fingerprint of the singularities that are generated in the binormal flow regarding corners. In fact, is this ODE, which is of Coulomb, with Coulomb ODE, because you have this the typical Coulomb potential. And how you end up obtaining this ODE, which is linear, by the way. But remember that once I have the constant, the curvature is constant, and that I know the torsion, then the problem is linear. So what you have to do is to compute the Fourier transform of the G and to do this renormalization. You do the math and you end up with this singular regular ODE that, by the way, in the initial equation is satisfied by two roots, 0 and 1. And that means that the difference of between the two roots is an integer, and then the classical theory tells you that at least one of the independent solutions has to have some kind of logarithmic behavior. So there is some kind of singularity intrinsic in this ODE. It turns out that the normal vector associated to the self-similar solution behaves well, but the binormal vector has a singularity in the Fourier transform side of logarithmic type. Anyway, so this is the picture of the self-similar solution. This was the horseshoe that appeared soon after the corners are generated, in the case, for example, of the equilateral triangle. And this is the angle that I was mentioning, that it was the difference between these terms examples and our example. When the angle goes to pi over 2, this angle tends to be, when the angle of the corner goes to pi, this angle tends to pi over 2. And this is the evolution. So this is the angle I am mentioning, and this is the evolution of the, say, the tip of the corner. So it goes here, creates the corner, and then there is a kink with, and this is the angle I was mentioning, goes in this direction. So this is the behavior of the self-similar solution. So now I am getting out of time. So let's try to tell you what is the math. So first of all, I have to solve the cubic NLS for this initial condition. And then the way of understanding it is by looking at the Fourier function, I mean the periodic function you obtain with these coefficients. So this is it. And I will need decay in this alpha case. So that means that the corresponding periodic function will be in some Sobolev space, and indeed S bigger than 1/2, so that it is an algebra. That's why this makes my life much easier. So back in 2018, Valeria and I proved a result of solving the cubic NLS. Here it is. And you have to make the right choice of the capital A of t, and it is nothing but the little L2. This is very reminiscent of the results of by Bourgain regarding the cubic NLS with periodic boundary conditions. And you have to fix the ansatz. The ansatz is that the corresponding solution has to look like as essentially the free solutions, right? And the only thing you modified are say the Fourier coefficients. And there is a problem with the resonances, and the very bad ones are the ones that are killed with this guy. So this A of t is absolutely crucial. And then once you kill the bad resonances, something that you are allowed to because of the geometry of the problem, then the whole thing becomes perturbative, and you can run a Picard iteration argument, and everything works out. But of course, this is solving the cubic NLS. Now you have to solve the evolution problem. I mean the geometric problem, and we did it. So you have to make given the angles, you find the coefficients, and this is the recipe, the relation between the angles and the size of the coefficients, and you construct a curve that it is regular for times which are not 0, but at time 0 is given by the polygonal line you have fixed. And of course, the rate of convergence is the one you expect, the one dictated by the self-similarity, which is the square root of t that appear already in Riemann's function. Okay, but we had a problem with these weights we needed in order to construct the solution, because in order to prove the theorem I mentioned, I really need polygonal lines that have many corners, a finite number of them, but all of them with the same size and with the same torsion. But I have infinitely many. So of course, this is growing, the weighted norm is growing, and then I will have a problem. But it turns out, okay, so this is the normalization condition. So all of them have the same size, but we have to go to 0 according to a free parameter theta. So we can fix the initial conditions at the origin with a given tangent vector. And this is what I had started to say, right? That because of the weights, we have to improve our result on the cubic NLS for this specific type of initial condition, and then we do it, and then we can solve the corresponding equation for the tangent vector. So this is this is what we obtain. These are the different geometries we obtain. For example, we can approximate the case of the particular solution of a straight line by taking polygons with more and more sides, and with the angles getting is closer and closer to pi. So at the end you obtain a straight line. But you could also do this, which is to create very much the kind of the movie we saw before. So I make as many copies as you want of a given of a given circle, and I put as many sides as you want. And at the end, I always have to continue these guys in two different lines. I could also approximate a straight line by, say, non-planar curves. And finally, I could also approximate the helices by polygonal helices with as many sides as I want, as I showed you in the movies before. Okay, so this is the kind of initial condition we we propose, and then what we obtain is that if you take the corresponding polygonal lines and you sum them by, and this is the scaling factor, then in the limit you obtain a specific Riemann's non-differentiable function, right? That lives in a plane. Moreover, for this, there is a tilde, and I will explain in a minute what is the meaning of this tilde. It depends on the torsion. If you don't have torsion, this is Riemann's function. If not, is the other ones I introduced before, and it will be written in a minute. Of course, the multifractal formalism is true. I mean, of course, we have to prove it. This is the new thing. And as I said, the case of the torsion-free, it's really nothing but Riemann's function, right? Which is this one. And in the case where it is not torsion-free, you have to put, instead of the quadratic faces, the ones given by an arithmetic progression. So this is the theorem. And okay, but what is our Riemann's non-differentiable function? In fact, our Riemann's non-differentiable function, it is not even Duistermaat function. It has this modification where, of course, when j equals 0, I have to understand there is L'Hopital limit, so it's a t coming on. So it's a small modification of a Riemann's non-differentiable function, but this is the one that really appears at the geometrical level. And this is the one that we obtain, which is very similar to the picture or the movie you saw. So of course you see again that coming from above or from below, you have two different tangents here. So then there is no tangent at this point. But what happened in the half of a period? You remember that in the case of Duistermaat, this spiral became two spirals, and the tangent was precisely one. However, the one that appears geometrically is this one, and there is only one spiral, and here there is no tangent because it is a spiral. In other words, we have proved that the multifractal formalism is true, very much as Jafar did, but in this nonlinear setting. The intermittency of Riemann's function has been recently proved by Borichev, Ezeizabarrena, and Darrocha in 2018. And the graph, in fact, this graph has no tangents, not as the one of Duistermaat, that there was a tangent here. And this has been proved by Ezeizabarrena in his thesis in 2019. So at the end, Riemann was right. So, as a conclusion, the theorem gives a non-obvious nonlinear geometric interpretation of Riemann's function. And I guess this is all. So thank you very much.